Retrosynthetic analysis. Retrosynthetic analysis is a method of working backwards from a target compound to starting materials. It is a technique for planning a synthesis, especially of complex organic molecules, whereby the target molecule, the complex target molecule, has been broken down into simpler structures called as the precursors along a pathway which leads to the identification of a simpler starting material or commercially available starting material from which the target molecule can be synthesized. Chemists always use these open arrows in order to write the retrosynthetic analysis. In designing a synthesis, reactions are often divided into two different categories. One is the formation of carbon-carbon bonds, and the other one is the conversion of the one functional group into another, which we call as functional group interconversions. Here are the different steps that we are going to follow in the retrosynthetic analysis. The first step is to compare the carbon skeletons of the starting material and product. And the next step is to concentrate on the functional groups present in the starting material and the product and to see what kind of interconversions we needed to perform. And the third one is working backwards from the product and forwards from the starting material. And the fourth one is to check the retrosynthetic analysis by writing it in the synthetic direction. Let's do our first example on retrosynthetic analysis and synthesis. How can we convert 1-butene to 3-hexanone? Now, the first thing is we needed to focus on the number of carbons on both the sides of the reaction. So here we have 4 carbons, but on the product side, we have a total of 6 carbons. So at some point, we have to make use of the acetylide ion formation where we wanted to form the carbon-carbon single bond. Also, we are going to think of a reaction where we can convert the triple bond into a ketone. So we're going to take this target molecule and then convert it into different precursors and finally arrive at the starting material from which this compound can be prepared. Let's draw the retrosynthetic analysis for this conversion. So we have 3-hexanone and we wanted to find the synthetic precursor for this molecule. If we have a carbon-carbon triple bond between these two carbons with a molecule which has exactly the same number of carbons, then we can easily form this compound by the acid catalyzed hydration of an alkyne. So the synthetic precursor for this molecule is going to be something like this, which is basically an internal alkyne. Now this internal alkyne has 2 extra carbons than the starting material, right? Now how can we synthesize this compound? What would be the synthetic precursor for this compound? Now, if you take a starting material and then add 2 carbons extra in the starting material by forming a new carbon-carbon single bond, then you can synthesize this, right? So there is definitely a way to synthesize this molecule from 1-butene, for which we can consider this is going to be another starting material. So these 2 starting materials are commercially available or simple starting materials from which we can synthesize it. Now let's write the actual synthesis for this conversion. So we have 1-butene. We are starting with 1-butene. And when you react it with NaNH2, it's going to give us an acetylide ion where NH2 minus is going to go grab this hydrogen and the electrons from the bond is going to go onto the carbon, forming an acetylide ion. And in the next step, this acetylide ion is going to make a nucleophilic attack on the other starting material, which is our alkyl halide. Since we need 2 carbons, we needed to choose ethyl bromide. So this is going to make a nucleophilic attack on this electrophilic carbon, thrust the electrons between the carbon and bromine onto bromine. Right? Now we have an internal alkyne which has exactly the same number of carbons as it present in the target molecule. And in the next step, when we do the acid catalyzed hydration of an alkyne, of an internal alkyne, it's going to give us a ketone. Since this is a symmetrical alkyne, symmetrical internal alkyne, it's going to result in only one product. Let's do the second example, and here the target molecule is Cis3 Hexing. So we have to find the suitable starting material for this. Okay, this is Cis3 Hexene, and if we have a triple bond here, then we can easily do the catalytic hydrogenation of the alkyne to convert it into an alkene, right? But what would be the synthetic precursor for this? We can have acetylene molecule as a synthetic precursor, because by converting that into acetylide ion and then reacting with the corresponding alkyl halide, we can convert this into this molecule. So let's work on the synthesis part. So we are starting with acetylene, and you're reacting with sodium amide with ethyl bromide, because you need to have two carbons here, right? Because when you compare the starting material and your final compound, it has got 4 carbons less, or 2 carbons on each side of the carbon-carbon triple bond. So you have to add those 2 carbons, for which we are going to use ethyl bromide. And the first step, it's going to put the new carbon-carbon single bond at one side of the molecule, and with repeating the reaction for one more time, it's going to also do it on the other side. Right, where the NH2 minus is going to go grab this hydrogen, and the bond between the hydrogen and the carbon is going to break, and it's going to move towards carbon, forming the acetylide ion. And that acetylide ion is going to make a nucleophilic attack on this electrophilic carbon, right? So basically it's going to synthesize this acetylide ion in the first step, and it's going to make a nucleophilic attack on this carbon, trusting the leaving group. So now you have this molecule right here, right? Now how can we convert this into this? How is it possible? Yes, we can simply do the catalytic hydrogenation. Now looking at this, for this we need a cis alkene, right? So for which we have to use Lindlar's catalyst. If we need a trans alkene, then we have to use sodium and liquid ammonia. But since we need the cis alkene here, we have to use a Lindlar's catalyst. So this is going to give us cis alkene. How can we convert ethyne into 2-bromopentane? Let's draw the retrosynthetic analysis for this compound. So let's take a target molecule, which is 2-bromopentane, and divide that into some simple synthetic precursors to arrive at the starting material. So if we can have a double bond here between these 2 carbons, then we can simply do the hydrohalogenation reaction. So the first synthetic precursor is going to be an alkene. Now how can we synthesize this alkene from something which has a triple bond? Yes, we can definitely do the catalytic hydrogenation. And what is a real starting material? So the ethyne is the starting material. Is it possible to convert an ethyne into this? Yes. So this is where we'll be making use of the acetylide ion. So this would be the starting material. Let's now work on the synthesis part. For the synthesis part, we have acetylene we have identified acetylene to be our starting material, right? And we are going to react it with NaNH2 first. With NaNH2, the NH2 minus is going to act as a base, abstracting this hydrogen right here, and it's going to break the bond between carbon and hydrogen to give the acetylide ion. So here is our acetylide ion. So once the acetylide ion has been synthesized, we needed to find out how many carbons we needed to put it in. Okay, so between ethyne and 2-bromopentane, we have 3 carbons less, right? So these are the 3 carbons that we needed to add in here. So therefore, we have to use propyl bromide. So this acetylide ion will act as a nucleophile on this propyl bromide to give us an terminal alkyne, which has exactly the same number of carbons as the target molecule. So these are the carbons that has been added, and it's right here. Okay, once we have this terminal alkyne, we wanted to do the hydrogenation, for which we are going to use the Linless catalyst. And we can convert this into an alkene. So the two hydrogens are getting added to these two carbons, which is losing one of the pi bonds. And once we get the alkene, we can do the hydrohalogenation, which is reacting with HBr to put the H and the Br on the two carbons, which is losing the pi bond. So according to Markovnikov's rule, the hydrogen is going to go to this carbon and the Br is going to go to this carbon to get our final molecule. How can we make this following interconversion possible? Let's take a target molecule and find the synthetic precursors for this molecule to arrive at the starting material. So this is our target molecule. And if you can imagine there is a double bond between these two carbons, then we can easily perform the hydroboration followed by oxidation reaction to put the hydroxyl group on it. Right? So this would be the starting material. The synthetic precursor for this molecule would be something which has a double bond between those two carbons. But how can we prepare this molecule from carbon-carbon triple bond? Simply by catalytic hydrogenation, right? So this would be the retrosynthetic analysis for this compound. So let's do the synthesis part. So we are going to start from the starting material and do a catalytic hydrogenation here. Here there is no preference. We can do the Linless catalyst, or we can use the sodium and liquid ammonia at minus 78 degrees Celsius, either one of those, right? So Linless catalyst or sodium or lithium in liquid ammonia at minus 78 degrees Celsius. Okay, either one of those. That's going to lead to the formation of an alkene. So once we get this alkene, we can perform the hydroboration followed by oxidation. So in the first step, which is the hydroboration, the electrophile is going to go to the carbon which has the most number of hydrogens. So the BH2 is going to go on here, and the hydrogen ion is going to go on to this carbon. And this is going to be synergistic, where the two groups are added exactly in the same direction. And in the next step, by reacting with sodium hydroxide and hydrogen peroxide in water, it's going to give us the corresponding alcohol. So if you do an acid catalyzed hydration here in this step, it's not going to put the hydroxyl group on this terminal carbon. Instead, it's going to put the hydroxyl group on this carbon. So we cannot perform an acid catalyzed hydration of an alkene here. Instead, we have to perform the hydroboration followed by oxidation. How can we perform this following conversion? So we have acetylene molecule which needs to be converted into Cis2,3 diethyl oxidine, which is an epoxide. Let's take our target molecule and find the synthetic precursor for that molecule. So how can we synthesize epoxide? Epoxides can be synthesized from alkenes, right? So if we have a double bond between these two carbons, then we can easily synthesize this epoxide. So that would be the synthetic precursor for this molecule. And you can see the two hydrogens are in the same direction, so therefore we have to take a cis alkene for this molecule. And how can we prepare this molecule, this alkene molecule? It can be definitely prepared from an alkyne which has exactly the same number of carbons, right? And that is through hydrogenation. So if we can definitely prepare this alkene molecule through the hydrogenation of this internal alkyne. And when we look into the starting material and the final products, we have 4 carbons less in the starting material. So we have to add enough carbons on each side of the carbon-carbon triple bond by using the acetylide ion formation and forming the new carbon-carbon single bonds, right? So first, this would be the synthetic precursor. And from here, we can use acetylene to create this molecule, right? So let's look into the synthesis for this molecule. So we have acetylene to begin with, and we are going to react it with NaNH2. And since this compound has 2 carbons extra, we have to add ethyl bromide to this. We are going to repeat the reaction for one more time to add the new carbon-carbon bond on the other side, to make sure that we have a total of 6 carbons in the final product. So in the first step, these 2 carbons were added, and this is the new carbon-carbon bond that's formed. And in the second step, these are the 2 new carbons that we added, and this one would be the new carbon-carbon bond that's formed. Okay, and in the next step, we are going to do the catalytic hydrogenation. And since we need a cis alkene here, right? So we need a cis alkene here, right? We have to specifically use the Lindlar's catalyst to give this cis alkene. And in the next step, the last step, we are going to use the peroxy acid to form the epoxide. The epoxide reaction is a syn addition where the 2 bonds are pointing the same direction. You cannot have an epoxide where the 2 bonds are pointing away from each other, right? Like it's impossible to create an epoxide in that way. How can you do the following conversion? How can you convert 1-butene into propanol? So this is propanol because it has got 3 carbons and you have an aldehyde, propanaldehyde, right? So when you take a closer look into this reaction, you can see that starting material has got higher number of carbons than the product. So which means the starting material needs to go through a process where it has been broken down into different compounds, where it can have fewer number of carbons in the products. So one of the reactions that we can think of where it's going to lead to the fewer number of carbons and also form the carbonyl compound is going to be ozonolysis. So what kind of compounds can undergo ozonolysis? And alkenes can undergo ozonolysis. So we needed to see whether we can convert this alkyne into an alkene at some point. So let's draw the retrosynthetic analysis for this target molecule. Let's write down the target molecule. And we need to have an alkene which has exactly the same number of carbons on each side of the double bond. Okay. So the alkene that we needed to start with should be something like this, where it has equal number of carbons on both the sides. When this alkene is subjected to ozonolysis, then it's going to give us this aldehyde, right, where it's going to break here. Now, what would be the synthetic precursor for this molecule? We can think of an alkyne which has exactly the same number of carbons as this and let it undergo hydrogenation to give this alkene, right? So the synthetic precursor would be this. And this compound right here can be easily prepared from 1-butene, which is a starting material. Okay, so let's take a compound which is 1-butene here, the starting material, and we'll perform the synthesis, in which case we are going to react it with NaNH2 first, which is going to create an acetylide ion where this is going to go and obstruct this hydrogen and put a negative charge on this carbon. Once the acetylide ion is created, then you can choose the number of carbons that you want. So the total number of carbons that you want in this alkene before it undergoes ozonolysis is total of 6 carbons. So we are lacking 2 carbons on one side of the carbon. So we are going to use ethyl bromide. So this acetylide ion will make a nucleophilic attack on this ethyl bromide to give us an internal alkyne. And once this internal alkyne is obtained, we can do the hydrogenation, right? Lineless catalyst. So that's going to put the 2 hydrogens on both the sides. So it's going to give us an alkene. And once the alkene is obtained, we are going to perform the ozonolysis followed by reduction with dimethyl sulfide, where it's going to cleave this molecule into 2 equal halves. And it's going to get converted into a carbonyl compound. So here in this case, it's going to be 2 molecules of propanol.